I'll talk about Lookup-Table Recurrent Language Models for long-tail speech recognition, a new architecture for language models that scales well. My name is Ronny. I'd like to thank Tara, Cal, Shankar, David, and Trevor for this research. Language models have a lot more data than speech models, such as the RNNT, because LMs require only unsupervised text corpora. The abundance of LM data can be used to train LMs that integrate with the RNNT to improve recognition on, especially on rare words, such as algo abe. Now, in order to leverage this large amount of LM data, the LM itself can't be too small because then it can't fit all of the data. A large LM, on the other hand, has the problem of excessive latency and ops in power, factors which make it hard to deploy. Our proposal is an LM architecture that scales up very well without increasing at all the latency or power. Let's start with the standard LSTM LM. It takes the current token and extracts an embedding of it and passes that embedding into the LSTM. Typically, to increase the LM size, you would increase the width or depth of the LSTM. We propose a different way to scale up. Our Lookup-Table Language Model introduces an auxiliary n-gram embedding table that embeds the n-gram of the previous n tokens. For example, if the current token is world, the n-gram of the previous tokens, or the bigram of the previous tokens, will be start of sentence hello. That bigram will be looked up to a unique embedding, which is concatenated with the standard embedding and passed into the LSTM the usual way. The advantage of this table is that it can be arbitrarily scaled up in the number of rows without increasing the latency, since the embedding lookup is a constant time operation. The retrieval also doesn't take much memory bandwidth at all, so this entire table needs not be stored on GPU memory. It can be stored on cheap RAM. Let's look at our results. The first row is the baseline standard LM. The second row is the same LM, but with our auxiliary lookup table. We achieve a 12% relative improvement in the WER, modest increase in flops, and a large increase in the number of embeddings, which again can be stored off chip. Comparing to a large LSTM scaled up in the usual way, we get about the same performance, but for 6x less the cost in terms of latency and operations. That's it for this 3-minute video. Please check out our paper for more. Thank you.